Hi, we move on to the next topic from quantum dynamics, the Schrödinger equation and its solution. In the last class, we discussed the time evolution operator, which is defined according to this equation. Here, u of t comma t0 is called the time evolution operator, and it is the operator that relates two states. One is the state of the system at time t equal to t0, or the initial state. This is the state of the same system at a later time t. And this is the notation that we used. So we said that get alpha comma t0 at later time t. This means that this is the state of the system at time t whose initial state or whose state at time t0 was get alpha. All right. So it's also the state at the time t0 is also defined as get alpha or simply get alpha comma t0. All right. So this is the state at the initial time t0, and here is the state at a later time t. And these two states are related by the time evolution operator. Okay. And based on conservation of information or determinism and reversibility, we said that this time evolution operator, actually we showed that we want the time evolution operator to be unitary. So unitarity is for conservation of information. Another important property satisfied by the time evolution operator was the composition property, which is given by u of t2 comma t0 is equal to u of t2 comma t1 multiplied by u of t1 comma t0. We said that we have to read this from the right to left. So first the state goes from time t0 to t1 and then from time t1 to t2. All right. So these two operations will give the evolution from time t0 to time t2. Okay. First, so in order to go from time t0 to t2, we can first go from time t0 to t1 and then from time t1 to t2. This is the composition property. Then we introduced the infinitesimal time evolution operator, which was given by u of t0 plus dt comma t0. Okay, so this operator takes the system or takes the state from time t0 to a slightly later time, an infinitesimally later time t0 plus dt. Right, and we looked at the form of this infinitesimal time evolution operator, and finally we said that we can write this as the identity operator 1 minus I h dt divided by h bar. H bar is the usual Planck's constant divided by 2 pi, and h we said has to be the Hamiltonian operator. And Hamiltonian operator is the operator that represents energy. Okay, that's the operator, the Hermitian operator that is related to energy. And we showed that in this form, the infinitesimal time evolution operator has the properties that we want it to have. We saw that the composition property is satisfied. We saw that the unitarity property is satisfied, etc. Now, using the composition property, we can derive the fundamental differential equation for the time evolution operator. Let's look at the time evolution operator u of t plus dt comma t0. Okay, using composition property, we can write this as the composition of the two operators u of t comma t0 and then u of t plus dt comma t. Okay, we can see that this is correct because this takes the state from t0 to t and this from t to t plus dt. Together we have the operator that relates the states at time t0 and t plus dt. Okay. All right. Now we know the form for the infinitesimal time evolution operator. We can write this as the identity operator minus I h dt divided by h bar. Okay. So here we have multiplied by u of t comma t0. Okay. We can actually multiply this. The identity operator multiplied by u of t comma t0 is simply u of t comma t0 and then minus I h dt divided by h bar multiplied by u of t comma t0. Okay, so on the left hand side you have got u of t plus dt comma t0, which is equal to u of t comma t0 minus I h dt by h bar u of t comma t0. All right, we could rearrange this and write u of t plus dt comma t0 minus u of t comma t0. You see that this is equal to minus I h dt divided by h bar u of t comma t0. Okay. So that's what we have here. u of t plus dt comma t0 minus u of t comma t0 is equal to minus I h divided by h bar dt u of t comma t0. Okay, we can write this also as u of t plus dt comma t0 minus u of t comma t0 divided by dt is equal to minus I h divided by h bar u of t comma t0. Okay, you know that this is better written as, because dt is an infinitesimal quantity, this is better written as limit delta t tends to 0 u of t plus delta t comma t0 minus u of t comma t0 divided by delta t is equal to minus I h divided by h bar u of t comma t0. Okay, so this is actually what this expression means. Okay, this is limit. In the limit delta t tends to 0, u of t plus delta t comma t0 minus u of t comma t0 divided by delta t. Now if you look at this, this is indeed the definition for a derivative. All right, so the left hand side, we know that the left hand side can be written as here. All right, this is simply partial derivative with respect to time of u of t comma t0. We write partial derivative because there's another argument in here, t0. All right, we are taking the derivative only with respect to time. If there was only one argument, you could write it as the full derivative or the total derivative. This is simply the partial derivative. Okay, so partial derivative with respect to time of u of t comma t0 is equal to, on the right hand side you have got minus I h divided by h bar u of t comma t0. Okay, you could multiply on both sides by IH bar. Okay, and you get IH bar partial derivative with respect to time of u. Okay, this is equal to h multiplied by Hamiltonian multiplied by u of t comma t0. Okay, so that's the equation that we have here. All right. Now this is called the Schrödinger equation for the time evolution operator. This is the fundamental equation that is obeyed by the time evolution operator. Okay. Everything that has to do with time development actually follows from this fundamental equation. Right? So the equation was IH bar partial derivative with respect to time of u of t comma t0 is equal to Hamiltonian multiplied by u of t comma t0. Okay. Now from this we can also obtain the Schrödinger equation for a state get. This is the Schrödinger equation for the time development operator. We can also get the Schrödinger equation for the state get. To get the Schrödinger equation for the state get, we take the Schrödinger equation for the time development operator and multiply on the right by get alpha comma t0, which gives us this equation. Now what is get alpha comma t0? Get alpha comma t0 is the state of the system at a fixed time t equal to t0. It's the initial state. So as such, the initial state does not depend on time. There's no time dependence in here, which means that this partial derivative with respect to time acts only on u of t comma t0 and not on get alpha comma t0, which means that we can take it inside to the derivative and write it like this. Okay, here also you can put a bracket if you like. Now what is u of t comma t0 acting on get alpha comma t0? We already know that u of t comma t0 acting on get alpha comma t0 is get alpha comma t0 at time t. It's the state of the system at time t. Okay, so this thing can be written as, whatever is in the bracket here can be written as get alpha comma t0 at a later time t. Here also we can write it. Okay, and we get the Schrödinger equation for the state get. This is called the Schrödinger equation for the state get. So to study the dynamics of the state, you can either work with this equation, the Schrödinger equation for the time development operator, or you could work directly with the Schrödinger equation for the state get. Now, if you can construct this equation and solve it, you get u of t comma t0. Once we have u of t comma t0, we know the action of it on the state get. All right, let's say the initial get. In that case, there's no need to bother with this equation. We can just work with u of t comma t0. In that case, our task would be to solve this equation for different situations and obtain u of t comma t0. Okay. So our first task is to derive formal solutions to the Schrödinger equation for the time evolution operator. And we'll treat three cases separately. The first and the simplest case is where the Hamiltonian operator is independent of time. By this we mean that even when the parameter time is changed, the Hamiltonian operator remains unchanged. For example, you could think of an electron in a magnetic field. We know that electrons have spin and they have spin magnetic moment, which means that the spin magnetic moment will interact with the external magnetic field. Now, if the magnetic field does not change with time, then the interaction does not change with time, and in such a situation, the Hamiltonian will be independent of time. The Hamiltonian will not depend on time. Okay. Now, if the magnetic field changes with time, then we say that the interaction also changes with time. In that case, we will have to use a time-dependent Hamiltonian. Okay. So the Hamiltonian for a spin magnetic moment interacting with a time-independent magnetic field is an example for a situation where the Hamiltonian does not depend on time. Now, if the Hamiltonian does not depend on time, the solution to this differential equation has a very simple form. It is exponential minus I h t minus t0 divided by h bar. Now let's look at this equation. If h was a number and u was some usual function that we are familiar with, then we know that the solution to this equation is in the exponential form because we have the derivative of a function which gives us a number multiplied by the same function. Okay, and exponential satisfies that property. But note that here h is not a number, it's an operator. U is also an operator. So the next question is, what do we mean when we say that there's an operator in the argument of the exponential? What do you mean by exponentiating an operator? Okay, the answer is that you have to interpret such expressions as a power series expansion. All right, because we know that normally exponential of x, the function exponential of x is defined by the power series 1 plus x square divided by 2 factorial, etc. Or compactly we can write this as sum over n equal to 0 to infinity x raised to n divided by n factorial. In the same way, if you have an operator on the exponential, you interpret this as the following power series: the identity operator plus a square divided by 2 factorial plus etc. Okay, or compactly we can write this as sum over n equal to 0 to infinity a raised to n divided by n factorial. Here a square or a raised to n, for example, a square means a multiplied by operator a. So whenever you see the exponential of an operator, you should interpret it as a power series expansion. Now our claim is that u of t comma t0 is equal to exponential minus I h t minus t0 divided by h bar is a solution to this equation. Okay, we have to check this, we have to prove this. We can prove this by using the power series expansion. So we look at this form of the solution, exponential, and we make a power series expansion. Exponential of minus I h t minus t0 divided by h bar is equal to the identity operator plus minus I h t minus t0 divided by h bar, the first order term. Right? We wrote that e raised to a is the identity operator plus a plus half a square plus etc. Okay, so the next term is half a square, where instead of a here we have minus I h t minus t0 divided by h bar. So this is the power series expansion. What we need to check is whether this solves the Schrödinger equation for the time development operator. So in order to check, let's take the time derivative. Let's take the time derivative of this exponential function. So taking the time derivative, let's write it like this: partial time derivative of exponential minus I h t minus t0 divided by h bar is equal to, we take the derivative on the right side, the derivative of the identity operator is 0, okay, plus what's the derivative of this term? We see that h does not depend on time, h bar also is a constant, so there's no action on these terms. Okay, so we have got minus I h divided by h bar, and the only derivative we need to take is of t minus t0. T0 is again a constant, so the only derivative is of t, which is 1. Okay, so the derivative, the partial time derivative of the first term is simply minus IH divided by H bar. What's the derivative of the third term here? So here we have a half here, and here is a square function. So the derivative of a square function is 2 minus IH t minus t0 divided by H bar. Okay, so this is the derivative of the square. We also need to find the derivative of whatever is inside here, which gives us again minus IH divided by H bar. Okay, minus IH divided by H bar is the derivative of whatever is in here. So let me write this as minus IH. Actually, I can pull this minus IH divided by H bar outside. Okay, and what we are left with is, here we are left with an identity operator plus this 2 and 2 cancel. Minus IH divided by H bar has been pulled out, and we are left with 1 plus minus IH t minus t0 divided by H bar. Okay. And of course, there are the higher order terms which we have not included here. Okay. Now, if you look at this, what we have here is exactly the first two terms of this power series, right? The identity operator minus IH t minus t0 divided by H bar, and we have the same term here. Okay. You could also try the third term, and you will see that you will get this term. Right? The third term here will also appear here if you take the derivative. But I think the idea is clear. We have the same power series in here, which means that partial derivative with respect to time of exponential minus IH t minus t0 divided by H bar is equal to minus IH divided by H bar. And then this is again the exponential function, exponential minus IH t minus t0 divided by H bar. Okay. So we see that the time derivative, the partial time derivative of exponential minus IH t minus t0 divided by H bar is equal to minus I divided by H bar, H multiplied by exponential minus IH t minus t0 divided by H bar. Okay, you can now multiply by IH bar on both sides, and we get IH bar partial time derivative of exponential minus IH t minus t0 divided by H bar is equal to, so if you multiply IH bar here, I multiplied by minus I is 1 and H bar cancels, so we have H, or the Hamiltonian, multiplied by exponential minus IH t minus t0 divided by H bar. Okay, and this is exactly the time, the differential equation or the Schrödinger equation satisfied or obeyed by the time evolution operator, the time development operator. Okay, so which means that exponential minus IH t minus t0 divided by H bar is indeed a solution to the Schrödinger equation, provided the Hamiltonian does not depend on time. So if the Hamiltonian depended on time, we would have derivatives of the Hamiltonian in here. Okay, and then we wouldn't get back the exponential. We wouldn't get back the exponential in this case. Okay. All right. Now, this form of the solution also satisfies the boundary condition. What's the boundary condition we are talking about? When t tends to t0, when t tends to t0, u of t comma t0 should go to the identity operator. Okay, because u of t0 comma t0 is equal to the identity operator. This is something that we discussed earlier. Okay, now we can show that the solution that we wrote down here actually satisfies this boundary condition. Okay, so our solution is u of t comma t0 is equal to exponential minus IH t minus t0 divided by H bar. Okay, you just put t equal to t0 here, and the argument becomes 0 and exponential 0 is equal to 1. So you see that u of t0 comma t0 is equal to the identity operator. Okay, because putting t equal to t0 in here will give a 0 in the argument of the exponential, and exponential of 0 is just the identity operator in this situation. Okay, so it satisfies also the boundary condition. The boundary condition is also satisfied because as t tends to t0, okay, our solution reduces to the identity operator. Now, just for a little bit more practice, Let's repeat the proof using the compact notation. Okay, so we have got exponential minus IH t minus t0 divided by h bar is equal to sum over n equal to 0 to infinity 1 by n factorial minus IH t minus t0 divided by h bar whole raised to n. Okay, because we said that e raised to a can be expanded as sum over n equal to 0 to infinity 1 by n factorial a raised to n. That's what we have done here. Instead of a, now we have minus I h t minus t0 divided by h bar. Okay, now let's take the partial time derivative of this series expansion. So you see that partial time derivative of exponential minus IH t minus t0 divided by h bar is equal to, if you look at this right side, the first term corresponding to n equal to 0 is the identity operator, and the time derivative of the identity operator is 0. So the derivative of the first term is 0. All right. Now let's sum from the second term onwards, from n equal to 1 to infinity. So you see that the summation is actually from n equal to 0 to infinity. We are taking the derivative. The derivative of the first term is 0. So we are writing it as 0 plus sum over n equal to 1 to infinity. The 1 divided by n factorial remains. And what's the derivative of this nth power? We know that if you have x raised to n, the derivative is n x raised to n minus 1. Okay, so that is n minus I h t minus t0 divided by h bar whole raised to n minus 1. We are taking the time derivative, so you have to multiply it with the time derivative of this, whatever is in here. What's the time derivative of this? It is minus I h divided by h bar. So multiplied by minus I h divided by h bar. Okay, this is the only thing that we have done. All right, so we have just used this formula. If you have e raised to x, and if you want to find d by dt, this is equal to, sorry, let's say d by dt of x raised to n. We can write this as n x raised to n minus 1, and then partial derivative of x with respect to time. That's all we have done here. Okay, so this is n x raised to n minus 1, and then partial derivative of x with respect to t. Okay, all right. Now we can slightly improve the notation here, because n divided by n factorial is actually, so if you look at this, we know that n factorial can be written as n multiplied by n minus 1 factorial. Okay, this means that n divided by n factorial can be written as n divided by n into n minus 1 factorial, which is equal to n divided by n minus 1 factorial. So n divided by n factorial is, so this becomes sum over n equal to 1 to infinity. N divided by n factorial is 1 divided by n minus 1 factorial. Okay, and here also we have minus I h t minus t0 divided by h bar whole raised to n minus 1, and we have got minus I h divided by h bar. Okay, since there is no n index, and since Hamiltonian does not depend on time, etc., we can just pull this out. So this becomes minus I h divided by h bar. Okay, now you see that this is the sum from n equal to 1 to infinity, but the first term here has n minus 1. Here also there is n minus 1, which means that we can redefine the summation index. We can define, let's say, m. We can introduce a new summation index. We can write m is equal to n minus 1. Okay, which means that when n equal to 1, n equal to 1 means m equal to 0, because m is n minus 1. So using this index, we can write minus I h divided by h bar sum over m equal to 0 to infinity. And what is n minus 1? It is simply m. So 1 by m factorial minus I h t minus t0 divided by h bar whole raised to m. Okay. Now you see that this is exactly the power series expansion for the exponential, right? It's exactly the same thing. So here we have used the summation index as n. Here we have used the summation index as m. So it's exactly the power series expansion for the exponential. So this can be written as, this is equal to minus I h divided by h bar, and what we have here is the power series expansion for the exponential, minus I h t minus t0 divided by h bar. Okay, and you see that the partial time derivative of this thing gives you minus IH divided by H bar exponential, the same thing. Okay, and the rest of the proof is exactly the same as before. Okay, so in a nutshell, exponential minus IH t minus T0 divided by H bar is indeed a solution for the Schrödinger equation obeyed by the time development operator, provided the Hamiltonian is independent of time. Okay. There's an alternative way to obtain the same solution. The idea that we are going to use is to construct the finite time evolution out of a large number of infinitesimal time evolutions. Okay. In other words, we can construct a finite time evolution operator we can build a finite time evolution operator out of an infinite number of infinitesimal time evolution operators. We already know the form for the infinitesimal time evolution operator. We can use this to construct any finite time evolution. Okay. So the idea that we are going to use is that a finite time evolution operator can be thought of as an infinite number of or a large number of infinitesimal time evolutions. Okay, infinitesimal time evolutions. So the idea we are going to use is the following. Suppose you have a finite time interval like this from between t0 and t. Okay, let's say that we know the state of the system at time t0. We need to know the state of the system at time t. The time interval here is actually t minus t0. Okay, so we have the state of the system at a given time. We need to find the state of the system at t minus t0 later, all right, after an amount of time t minus t0. So what we are going to do is that we can divide up this time interval into a large number of equal intervals. All right, let's say that we are dividing this up into capital n equal intervals. All right, so we can divide this time interval into, let's say, n equal intervals. Okay, there are n divisions. Okay, there are n divisions like this. Now each of this division will correspond to a time interval t minus t0 divided by n, because we have divided up the time interval t minus t0 into n equal parts. Okay, now if you take the limit n tends to infinity, okay, then this t minus t0 divided by n can be written as an infinitesimal amount of time, dt. So in the limit where n goes to infinity, t minus t0 divided by n can be called an infinitesimal time interval. Okay. Now we can construct the time evolution corresponding to the interval t minus t0 out of n, okay, out of n infinitesimal, out of n infinitesimal time evolution operators. Time evolution operators. Okay, this is the basic idea. All right, and n, we are taking the limit where n goes to infinity, so that this interval can be considered as an infinitesimal interval. Okay, so we take the transformation from here to here. Let's say that that's one infinitesimal transformation, and then from here to here, and then from here to here, like that. If you compound such infinitesimal transformations, you can obtain a finite, uh, finite in finite time evolution. Okay, that's the idea that we are going to use. Okay, so which means that we can write u of t comma t0 is equal to, all right, we take the limit n tends to infinity, so that we can use the result for the infinitesimal time evolution operator. Okay, and 1 minus the form of the infinitesimal time evolution operator was the identity operator minus IH divided by h bar dt. Now here instead of dt we have t minus t0 divided by n. Okay, now this is just one operator corresponding to one infinitesimal time evolution. All right, we need to compound n such time evolutions, so you have to take this time evolution n times. That will give the finite transformation from t0 to t. This is the basic idea that we are using here. Okay, I hope this is clear. All right, now we can use this result. Limit n tends to infinity, 1 plus x by n whole raised to n is equal to e raised to x. All right, we shall prove that shortly, but right now let's directly use this result. Okay, So directly using this result, you see that in the place of x divided by n, here we have minus IH divided by h bar t minus t0 divided by n. So this is what we have in the place of x, right? In the place of x here, what we have is minus IH divided by h bar t minus t0. Okay, so if you take this result, if you use this result, this is equal to, you can write this is equal to exponential of, okay, x, what's x, minus IH divided by h bar t minus t0, okay, which is exactly the result we have here. So you can either solve it directly, or we can construct the finite time evolution operator out of an infinite number of infinitesimal time evolution operators. That's what we have done here. Okay, so basically we are using the composition property. We are assuming that, or we are considering the finite time evolution as a composition of an infinite number of infinitesimal time evolutions. Okay. Now, I hope this is clear. I think we have already proved this when we discussed what do you say? I think when we discussed space translations. I don't remember exactly. Anyway, let's prove this result just for the sake of completeness. Okay. So let's start with the right hand side. Let's look at limit n tends to infinity 1 plus x divided by n whole raised to n. Now when n tends to infinity, that means that this x by n here is very small. We can use the binomial expansion. The binomial expansion says that we know that if x is small, 1 plus x whole raised to n is equal to 1 plus nx plus n into n minus 1 by 2 factorial x square plus etc. This is called the binomial expansion. So let's use the binomial expansion here. This will become 1 plus n multiplied by x divided by n plus n into n minus 1 divided by 2 x by n square plus etc. Right? So let's consider just these three terms. You can, if you want, you can consider also the next term for practice. Now this is equal to 1 plus x, because the n cancel here, okay, plus n into n minus 1 divided by 2 x square divided by n square. Now one of the n will get cancelled, so you can write this as 1 plus x plus n minus 1 divided by 2 and multiplied by x square divided by n. Okay. Now you can rearrange this a little bit. You can write this as 1 plus x plus 1 by 2. This term can be written as n minus 1 divided by n. You can write it as n by n minus 1 by n. And we also have the x square here. All right. Of course, you have to take the limit. We have to take the limit n tends to infinity. Okay. We are doing this in the limit n tends to infinity. There are other terms which we neglect. We don't neglect, we don't include it in here, that's all. Okay, so this is equal to 1 plus x plus, okay, so half n divided by n is 1, 1 minus 1 by n x square plus etc. plus the higher order terms. Okay. Now let's take the limit n tends to infinity. Okay, remember, we are talking about the limit n tends to infinity. If you take the limit n tends to infinity, this term becomes 0 because it's 1 by n. In the limit n tends to infinity, 1 by n becomes 0. So this is 1 plus x plus 1 by 2 x square plus etc. Now what is this? This is exactly the series, power series expansion for e raised to x. Now if you look at the next term, you will find that in the limit n tends to infinity, the next term will become x cubed divided by 3 factorial, and the next term will become x raised to 4 divided by 4 factorial plus etc. So we have the binomial expansion for e raised to x. So we see that this is equal to e raised to x. Okay. So that's what this result means. E raised to x can be written as limit n tends to infinity 1 plus x by n whole raised to n. And we have used this result here. Okay. And using this result and constructing the finite time evolution out of infinitesimal time evolution operators, we get the same result. Okay. The second case is where the Hamiltonian operator is time dependent, but the Hamiltonian at different times commute. We'll see why this condition is important. Now, an example for this is the situation of the spin magnetic moment in a magnetic field whose strength varies. Right, the strength of the magnetic field will vary with time, but whose direction is always unchanged. Okay, this would be a case where the Hamiltonian is time dependent and also the Hamiltonian at different times commute. In this case, the formal solution is given by u of t comma t0 is equal to exponential minus I divided by h bar integral t0 to t dt prime h of t prime. So here t prime is the integration variable. We integrate this and you get a function of t. Okay. Now, when the Hamiltonian does not depend on time, we saw that u of t comma t0 has the simple exponential form. Okay. Here we have a slightly more general result. We can show that this result reduces to this result when the Hamiltonian does not depend on time. So let's do that first. Right? So you start with this result. Now suppose the Hamiltonian has no time dependence, then we can write this as exponential minus I divided by h bar integral t0 to t dt prime. Now, since the Hamiltonian does not depend on time, we can actually pull it out. If the Hamiltonian does not depend on time, we can pull it out of the integral over time. So that would become exponential minus IH divided by h bar. What is integral t0 to t dt prime? It's simply t minus t0. Now, which is exactly the result we had before if the Hamiltonian is independent of time. Okay, so we see that the result that we have written down here, the solution that we have written down here, includes our previous solution as a special case. Okay, it includes the previous solution as a special case. So that is suggestive of the fact that this indeed is the correct generalization, right? But that's not enough. We actually have to prove that this solution actually works, or we have to show that this expression for u of t comma t0 actually satisfies or actually obeys the Schrödinger equation for the time evolution operator. That's what we are going to do next. So let's now show that this expression for the time evolution operator indeed solves the Schrödinger equation for the time evolution operator, provided the Hamiltonians at different time commute. This is what we want to show. So again, we'll use the power series expansion. So we can write exponential minus I divided by h bar integral t0 to t dt prime h of t prime is equal to, we'll use the power series expansion. First is the identity operator. The second term is, so if you have e raised to a, you can call this as a. If you have e raised to a, it's 1 plus a square by 2 factorial. Right? So 1 plus a is minus I divided by h bar integral t0 to t dt prime h of t prime. Okay, and the next term would be 1 by 2 and then the square 1 by 2 a square. Square will write, for the moment we'll write the square as integral t0 to t. So it's this minus I by h bar, then integral t0 to t dt prime h of t prime. Okay, and this term squared. All right. Now let's take the time derivative of this. Let's take the time derivative of this. So let me write the time derivative, the partial time derivative of exponential minus I divided by h bar integral t0 to t dt prime h of t prime. Okay, this is the derivative of the first term is 0. All right, and the second term, let me write it as minus I by h bar partial time derivative of the integral t0 to t dt prime h of t prime. Okay, plus half time derivative of the square of this integral. Okay, so I think this minus I by h bar square I can take outside. Oh, no need, we can just write it like this, minus I by h bar, so missed the partial derivative, partial time derivative of minus I by h bar. So this square, this is the square of an integral. All right, so we can write it as the product of two integrals, And just as we do it when we square a summation series, we would use different dummy indices. Okay, so when we write the product of the same integrals, we have to use different different notation for the variable of integration. Right, otherwise we would be missing some terms. Right, so we can write this as minus I by h bar integral t0 to t dt prime h of t prime. That's this integral once. Okay, we need to multiply it with the same integral, but we'll use t double prime as the integration variable. It doesn't matter what we write here. Okay, it doesn't matter what we write here, because in the end we'll integrate this and then substitute the limits. So whether you write t prime or t1 or t double prime, anything inside this, it gives the same result. Okay, so when we are squaring this, this becomes integral. There's again this minus I by h bar. So maybe I should put a bracket here. That's the integral once, and then minus I by h bar integral t0 to t. We'll write this as dt double prime h of t double prime. Okay, so we have to use the product rule here. When we take the derivative, we have to use the product rule. That's the idea. Okay. All right. So let's take the derivative now. The first term is, now I'll write here to save place. So this is 0. 0 we don't have to write. What's the first term? We have got minus I by h bar. And this is the time derivative of the integral. Okay, this is the derivative of the integral over time. Okay, now we can use the fundamental theorem for calculus, which says that, let me write it here. If you have something like the derivative of integral, let's say x0 to x, f of x prime dx prime. Okay, so since the integral is also called as an antiderivative, okay, this should give us simply f of x. So this should simply give us f of x. This is the fundamental theorem of calculus. I think it's called the fundamental theorem of calculus. You can check. All right. So you integrate this, you get a function of x, because the upper limit is written as x. Right. The upper limit is written as a variable, not a number. So this gives a function f of x. Now, after integrating, if you take the derivative again, you will get back the old function f of x. Okay, this is the fundamental theorem for calculus. Fundamental theorem of calculus. All right. So this term would simply become h of t. All right. So the derivative of this integral will simply become h of t. Now let's look at the second term. Plus half. Now we have to use the product rule. Okay. So we'll take the derivative of the first term, derivative of the first term multiplied by the second term, and then first term multiplied by derivative of the second term. That's the product rule. Okay, so let's write it like that. This becomes 1 by 2 minus I by h bar. Again, let's take the derivative of the first term. Using the fundamental theorem of calculus, you get this as h of t, and the second term remains the same, minus I by h bar integral t0 to t, okay, dt double prime h of t double prime. Okay, now there's also one more term. Let's write it as 1 by 2. The first term, minus I by h bar t0 to t dt prime h of t prime multiplied by the derivative of the second term. All right, so that would be minus I by h bar. What's the derivative of this thing? Again, we use the fundamental theorem of calculus, and you get h of t. Okay, plus etc. So this is, you see that we can write this as minus I by h bar h of t plus half minus I by h bar square h of t multiplied by integral t0 to t dt double prime. So since we don't have anything else, we can simply write this as dt prime. Okay, this is the integral. Here the index or the variable of integration is written as t double prime, but since we don't have anything else in this, we can as well write this as t prime. We are just renaming the variable of integration. Okay, so it's just like the dummy index that we have in a summation series. So this is dt prime h of t prime plus, let's write this as half Again, we have got minus I by h bar square. Okay, minus I by h bar square, and integral t0 to t dt prime h of t prime and h of t. Okay, so this is where we are. We started with exponential minus I by h bar integral t0 to t dt prime h of t prime, and we found the partial time derivative. Okay, we used the power series expansion, all right, and we got the result, or we obtained the result up to this point. Okay, now in order to continue, we see that there is the h of t here, there is an h of t here. So as usual, we can pull out this minus I by h bar h of t, and the rest is supposed to be the exponential. Okay, the power series expansion for the exponential. All right, but there's a small problem here. The h of t here is on the right side, not on the left side. Right, at this point it's fine, but in this term the h of t is on the right side. Okay. Now in order to pull this h of t out, we have to assume that h of t commutes with h of t prime. If h of t does not commute with h of t prime, then we cannot bring this h of t to the left. Right? This is why we gave the condition that the Hamiltonian at different times has to commute if this solution has to work. Okay. Now provided the Hamiltonian at different times commute, okay, we can write this as partial time derivative of exponential minus I by h bar integral t0 to t dt prime h of t prime is equal to minus I by h bar h of t plus half minus I by h bar square h of t integral t0 to t dt prime h of t prime, okay, plus, now using the fact that Hamiltonian at different times commute, we can bring this h of t to the left, all right, since it commutes with h of t prime. So this would become plus half minus I by h bar square h of t, and then integral t0 to t dt prime h of t prime. Okay, now we can get the result, desired result. This is equal to, let me pull out this minus I by h bar h of t. This is pulled out. Okay, and we are left with 1 plus, so here we have got half, so we have pulled out 1 minus I by h bar h of t. Okay, so here we have got half minus I by h bar, because there's a square here, one of it I have pulled out, so we have got half minus I by h bar h of t integral t0 to t dt prime h of t prime. Okay, again here we have got half minus I by h bar. Okay, oh sorry, there's no h of t here because we have pulled it out. Let me correct it. So this is half minus I by h bar integral t0 to t dt prime h of t prime plus half minus I by h bar integral t0 to t dt prime h of t prime, and there are other terms which we have not included. Okay, so this is equal to minus I by h bar. We see that these two terms are exactly the same, so we can add them up. Okay, so you get minus I by h bar h of t, the identity operator, plus this becomes minus I by h bar integral t0 to t dt prime h of t prime. We have just added these two, half plus half is 1. Okay, plus etc. There are other terms. Now if you look at this, this is exactly the first two terms in the power series expansion for exponential minus I by h bar integral t0 to t dt prime h of t prime. Okay, you can check the other terms, it will follow. Okay, so this is equal to minus I by h bar h of t exponential minus I by h bar integral t0 to t dt prime h of t prime plus, sorry, there's no plus, this is exponential, so it's the full series. Sorry. Exponential minus I by h bar integral t0 to t dt prime h of t prime. Okay, what is this? This is the partial time derivative of exponential minus I by h bar integral t0 to t dt prime h of t prime. Okay, now, so I have made some space here. This is where we are at. We found that partial time derivative of exponential minus I by h bar integral t0 to t dt prime h of t prime is this. Okay. Now again, as usual, you multiply by I h bar on both sides and you see that I h bar exponential, I h bar partial time derivative of the exponential integral t0. So there's this minus I by h bar integral t0 to t dt prime h of t prime is equal to, so when I multiply by IH bar, you see that on the right, you get h of t exponential minus I divided by h bar integral t0 to t dt prime h of t prime. Okay. So you see that this is exactly the Schrödinger equation for the time evolution operator. Okay, IH bar, the Schrödinger equation for the time evolution operator was IH bar partial time derivative of u of t comma t0 has to be equal to h u of t comma t0. So we see that our result, this exponential, satisfies this differential equation provided the Hamiltonian at different times commute. The Hamiltonian at different times commute for t not equal to t prime. Okay, this condition was important, otherwise we wouldn't get this. Okay, so this is case 2. If the Hamiltonian at different times commute and if the Hamiltonian is time dependent and the Hamiltonian at different times commute, then the solution can be written in this form. You can write u of t comma t0. Let me just repeat it. U of t comma t0 can be written as exponential minus I by h bar integral t0 to t dt prime h of t prime. Okay. All right. We have been trying to find formal solutions to this equation. We considered two cases already, one in which the Hamiltonian did not depend on time, and the second case was the Hamiltonian depended on time, but the Hamiltonian at different times commuted. Okay. The third case is where the Hamiltonian depends on time, but the Hamiltonian at different times do not commute. So we don't have h of t, h of t prime equal to 0 for, so we can say that h of t, h of t prime not equal to 0 for t not equal to t prime. Now we already saw that in this condition, our previous solution will not work. Okay. Now, if you want an example for such a situation, you can think again of the spin magnetic moment in an external magnetic field. All right. In this case, the magnetic field direction also changes with time. So suppose the magnetic field direction is changing with time. Okay. At a particular time t equal to t1, let's say that the magnetic field is in the x direction, and at a later time it's in the y direction, etc. In this case, it can be shown that the Hamiltonian is time dependent and also the Hamiltonian at different times do not change. The reason is that we'll see this later. In such a case, the Hamiltonian goes like, the interaction Hamiltonian goes like s vector dot b vector. Okay. Now let's say that initially b vector is along the x direction and then s vector dot b vector would go like sx. All right, and at a later time, if the b vector changes to the y direction, then s vector dot b vector would go like sy, and sx and sy do not commute, as we have already seen. So this would be a case where the Hamiltonian at different times do not commute. Okay, so because sx and sy do not commute, h of t1 and h of t2, which go like s vector dot b vector, do not commute either. Okay. The formal solution in such a situation is given by this power series. This power series has a name. It's often called the Dyson series. Now, here we shall not see how this power series can be obtained. I think we'll be doing it in one of our later classes when we discuss what's called the interaction picture of time evolution. Right? Over there in a slightly different context, we'll see how such a series can be obtained. Okay. The only thing we'll do here is to check whether this actually solves the Schrödinger equation. Okay. One thing to note is that in our previous two cases, we could write the formal solution as an exponential, but this series cannot be immediately written as uh, written as an exponential. Okay. There is actually a slightly roundabout way of writing this in the exponential form, but we shall not discuss it here. Let's just see if this series actually satisfies the Schrödinger equation. In order to do this, we can look at a few terms in this power series. Okay, so you see that u of t comma t0 is 1 plus. Now let's look at the n equal to 1 term. N equal to 1 term is minus I by h bar whole raised to 1. Okay, and there's, if you look at this expression, there are a large number of integrals. Okay, now the last integral corresponds to n, dtn. So if you take n equal to 1, we only have integral dt1. So the first term would be integral t0 to t dt1. Okay, the other integrals are not here because we are taking only the n equal to 1 term. Okay, and then of course you have to include this h of t1. This is the first term of this power series expansion. What's the second term? It's minus I by h bar square. Okay, so you're looking at the n equal to 2 term. So it would be minus I by h bar square. You see that the integral should go from t0 to t and the dt1, t0 to t1, dt2, because we have to go up to dtn. Okay, so the n equal to 2 term would be integral t0 to t dt1, integral t0 to t1 dt2. Okay, so we have reached up to n equal to 2, and then we have got h of t1, h of t2, plus etc. and the higher order terms. Okay, let's just work with these three terms. Now if you find the, let's find the partial time derivative of u. The first term, the derivative gives 0, and then it's minus I by h bar, partial time derivative of this integral, integral t0 to t, dt1 h of t1 plus minus I by h bar square, partial time derivative of integral t0 to t dt1, integral t0 to t1 dt2 h of t1 h of t2, goes on like that. Okay, let me just put a bracket in here. That is, we first have to carry out this integration, and whatever result is obtained, it has to be integrated over t1 also. Okay, that's the idea. Now the first term is 0, so we can leave it. What's the second term? Again, we can use the fundamental theorem of calculus. We have the partial time derivative of an integral, uh, integral dt1 h of t1. Okay, so we said that, we talked about the fundamental theorem of calculus, which said that if you have something like this, partial time derivative of integral t0 to t dt1 f of t1. Okay, this is simply equal to f of t. Okay, in other words, this is simply equal to f of t. This is simply equal to f of t, which means that the integration vanishes. Okay, and t1 is replaced by t. The upper limit here is t. Okay, so using that result, you see that this is equal to minus I by h bar. Okay, this would simply be, using the fundamental theorem of calculus, this would simply be h of t. Okay, and the next term minus I by h bar square. Again, we see that this is exactly of the same form, partial time derivative of integral t0 to t dt1 f of t1. Only f of t1 is now this integral. This is f of t1. Okay, so this partial time derivative of this integral has to be equal to f of t. What is f of t? You just take this function and put t1 equal to t. Right? So this integration will vanish and you will get integral f of t. All right. So you take wherever t1 appears, you have to substitute by t. So this would be integral t0 to t. See here it's t1, but when we use the fundamental theorem of calculus, this t1 will become t. This integration has gone. Okay, so this is integral t0 to t, and then dt to h of, there's an h of t1 here, which we write as h of t, okay, because of this fundamental theorem of calculus, and then we have got h of t2 plus etc. Okay, let's continue. This is where we are. We started with the first few terms of the Dyson series. These are the first few terms. We found the time derivative and we wrote it in this form. We just used the fundamental theorem of calculus and we wrote it like this: minus I by h bar h of t minus h bar I by h bar square integral t0 to t dt to h of t2 plus etc. Okay, now we can write this also as minus I by h bar h of t plus minus I by h bar square integral t0 to t. We see that this t2 is used as a variable for integration. It's just like a dummy index in a summation series. So we can simply write this as dt1 h of t1. We have just changed the variable of integration. Okay, we have not we have just used we have just used a different notation for the variable of integration. That's more correct way of saying it. Okay, just like using a different dummy index, whether you write dt2 here or dt1 here, after integration that will disappear, and then we'll apply the limits. Okay, so it doesn't matter whether you write dt1 dt2 or dt3 in here. So we can write it like this. Now we see that the integration is over t1, so h of t can be pulled out of the integral. So we can write this as minus I by h bar h of t, which is common, and then the identity operator, plus minus I by h bar. One of minus I by h bar here is taken outside. This h of t is also pulled out. Okay, so this is minus I by h bar integral t0 to t dt1 h of t1 plus etc. Okay, so you see that whatever is in the bracket is exactly the first few terms of this power series expansion. Actually, it's the first two terms of this power series expansion. The identity operator plus minus I by h bar, okay, integral t0 to t dt1 h of t1. Okay, integral t0 to t dt1 h of t1. All right, we can actually show that the same follows for the other terms. The other terms also will follow if you do the same procedure, if you go through the same procedure. Okay, so we see that when you take the partial time derivative of this form of the for u, you get minus I by h bar h of t multiplied by the same series. Okay, now you do the same thing, you multiply by ih bar on both sides. You see that ih bar, partial time derivative of u, is equal to h of t multiplied by, this is again the form of u that we started with. Okay, this is the form of u we started with, h of t multiplied by u of t comma t0 to be precise. Okay, so what we see is that what we showed as the Dyson series indeed satisfies the Schrödinger equation for the time evolution operator, because this is indeed the Schrödinger equation for the time evolution operator. Okay, the series solution that we saw now is called as the Dyson series, as I mentioned. It's named after Freeman Dyson. He developed this when he was doing quantum field theory. We'll see how such an expression can be obtained in one of our later classes. Okay, and in elementary applications that we do in this chapter, we shall be discussing only case 1. Case 1 is where the Hamiltonian is time independent, and we can write the time evolution operator in this simple form: exponential minus I by h bar h multiplied by t minus t0. Okay, we shall be using only this form in this chapter. Okay, let me just summarize what we have seen in this session. Okay, we obtained the Schrödinger equation for the time evolution operator. We saw that the time evolution operator has to satisfy this equation. Is equal to h multiplied by u of t comma t0. So this is the differential equation or the Schrödinger equation for the time evolution operator. Given the Hamiltonian, you can write this equation and solve it. Once you have u of t comma t0, you can find the ket at any later time using this equation, u of t comma t0 acting on ket alpha comma t0. Okay. Now we also obtained the Schrödinger equation obeyed by the state ket, but we said that we won't be using that immediately. We shall work with the Schrödinger equation for the time evolution operator. Okay. And then we looked at the formal solutions for this Schrödinger equation in three different cases. Okay. In the first case, we talked about the situation where the Hamiltonian does not depend on time, and then the time evolution operator has this form: u of t comma t0 is equal to exponential minus I by h bar, h multiplied by t minus t0. Okay. We then talked about a case where the Hamiltonian depended on time, but the Hamiltonian at different times commuted. In that case, u of t comma t0 also has this simple form or simple exponential form. It is minus I by h bar integral t0 to t h of t prime dt prime. Okay. Now, if the Hamiltonian at different times do not commute, then we have a slightly more complicated form, which we do not immediately write in the exponential form. And this series solution was called the Dyson series. Okay. And we concluded by saying that in this chapter, we shall be using only the first form. Now with that, I shall conclude this session. Thank you.